Good morning, everyone. First, I really want to thank Kathy and all the NERSIC organizer for this meeting for inviting me. It has been really a pleasure to be here. First time for me here in Berkeley, also in general. So I'm really happy to be here. My talk today is I'm going to speak about quantum accelerated supercomputing and for battery material simulation. So my talk is really divided in two parts. First, I will explain what NVIDIA is doing in the space of the quantum accelerated supercomputing, and I will show you is one of the applications that I'm currently working on for battery material. So first is that NVIDIA is not building any quantum hardware. So that's something I want to clarify because many people asked me about that yesterday. But what we are building at NVIDIA is that we are building an accelerated quantum supercomputer. So what is that accelerated supercomputer? It is the AI supercomputer that we are building in NVIDIA using GPU integrated with the quantum process unit. So in this case, NVIDIA is building this to be de-risk as a quantum hardware. So it's going to be agnostic for any quantum hardware we are that the quantum provider are going to provide. It's going to be working nicely for this hybrid application. So we know that in future, all application is going to be hybrid. So in that case, you can use build your application such as a part of it can be run on GPU, part of it can be run on QPU, so that you can take advantage of the hardware you have in your supercomputer. And we are building all the infrastructure and library needed for that. So for that, NVIDIA is building we're working to develop this CUDA-Q platform, which is really suitable for these hybrid applications. And as I will show you how CUDA-Q is also how it looks like in few slides. So you might ask, so do we really need that quantum computing needs a GPU? So there are two areas where we see like GPU is useful for quantum computing. One is really GPU for quantum computing for research, and another is also for running the quantum hardware itself. So for research, as you know, most of the time, like nowadays, all quantum hardware are noisy, so we always use a classical simulator. So in that case, you can use GPU to accelerate your for simulating your quantum circuit, and it also tests the quantum, like the circuit, scalability of this circuit using the GPU. Also, you can use it for circuit design. So you have been seeing recently a lot of paper where people will start to also use AI for generating quantum circuit, like for example, the work by Alan, where they do use this generative quantum eigensolver. Also, you have seen recent paper, also they have started to use AI not just for generating quantum circuit, but also for unitary synthesis to decompose a given unitary operator into an elementary gate and so on. So there has been a lot of AI now to use to really doing this work for circuit design. It also can be used for designing the quantum hardware. So we need to really do some simulation and dynamical simulation for this quantum hardware. And that's also where also GPU can help here and so on. GPU also can be used for running the quantum hardware. So we need error correction for this hardware. And also in that case, you need to keep sending information from the quantum to the classical hardware. And this is also where GPU can be used also to accelerate that. And it's also nowadays also AI start to use for calibrations, readout, and so on. And that's also where GPU can be quite helpful here for running this quantum computing. So that is where GPU, NVIDIA is collaborating with Quantum Machine to design this DGX Quantum, where we're integrating both the GPU and the quantum hardware together to accelerate this quantum error correction, error calibrations, and all the hybrid applications. And it's, as I said, it's a hardware agnostic. So it's going to be working for different hardware. And with the GPU, we have observed that with the latency, we have observed like 1 to order of magnitude less than the other traditional approach. So here is some data we have done with the quantum machine about the latency when we use the GPU for the DGX quantum compared to other approach. So here's these results. Here, this 400 is sending information in one direction from the quantum to the classical or the other. So it's one direction only. So this is 400 nanosecond. And we'll see with different hardware also for the GPU. So there will be more data is coming out about that. So in addition to that, we also need to build the platform that can be useful for using this kind of hybrid applications. So we are building this CUDA-Q stack. So CUDA-Q is in the front end. It allows you, this is where the user can build their own applications. It can be in C++, it can be in Python. And then in the middle layer here, we are also have this compiler, which can compile your code from a high-level language to the lower language. So here we use the MLIR and the QIR. And in the back end here, you have it can be run on quantum hardware. So as I said here also, we are quantum hardware agnostics. So we work with different quantum providers to allow executing the CUDA-Q the CUDA-Q code into quantum hardware. And also, if you don't have access to quantum hardware, you can also do this on a classical simulator. And we are doing this by integrating this cuQuantum library in the back end of the CUDA-Q so that it can be executed also on a GPU. And we are allowing their different simulator. So you have a state vector, you have also tensor network and MPS. And also we are recently, you probably have seen in the news, we added also the CoDynamics library. So there is a dynamic library now where you can also add some noise and also test this with noise and without noise. The advantage also of using CUDA-Q is that it uses this CUDA-Q programming, which is like the kernel-based programming language, which allow you to really use, in this case, the quantum circuit as a kernel and integrate it tightly with also the existing classical programming, parallel programming. So in that case, as I said, you can really run applications in like you build your applications. Part of it can take advantage of GPU accelerations. And another part is in the kernel in your code can be run on quantum hardware. There is many impact for the quantum computing. So there are many applications, some of them like for EV, for drug discovery, logistics, machine learning, and NVIDIA is working with a lot of people in the industry to explore all these use cases. And today I will mainly focus, I will only focusing on this EV chemistry for battery. So what is the battery and what's the problem here in battery? So battery is made of two electrodes and electrolyte. So during the discharge of the battery, the lithium ion moves from the anode towards the cathode through the electrolyte, and the electron moves through this external circuit to perform an electric work. And during the charge of the battery, you apply a voltage, external voltage, which pushes the lithium ion from the cathode back to the anode. When you design the battery, you have to have the electrodes must be post-ionic and electronic conductor, but the electrolyte must be only ionic conductors, but not its insulator to electrons. Now, for the EV to replace all the gasoline power transportation, there is a lot of improvement needed in battery. For example, two of the most important concern about customers is the driving distance as well as the charge rate of the battery. So this is very challenging. It might seem like, okay, can't we just change the material? And especially people in industry know how to increase the charge or how to improve the charge or how to even increase the driving distance. The problem is that the material has to be designed in a very optimum way. So in that case, actually, to maintain the thermodynamic stability of the material, you must have the voltage window of the electrolyte within the voltage window of those, or located within the Fermi energy level of the cathode and the anode. If you don't do this, then you break the thermodynamic stability of the battery, and this is cause really a huge problems in battery. So one of these problems is that what they call it the electrolyte decompositions. So what happens is that when the electrolyte when you assemble your battery and have your electrolyte and your electrodes get touched, then what happens is this electrochemical reaction happens that electrons moves from the electrode to the electrolyte, which causes decompositions and decompose your electrolyte. So that causes a consumption of your active material. And the worst case thing is what happens is that cause actually layers. So when this decomposed, it forms some chemical structure that actually aggregate on the electrode, which affect the movement of the lithium ion when it's go back and forward. And also this is actually cause some gases that cause pressure inside the battery, and with high temperature, that's also one of the reasons can cause fire inside battery when you are driving. And also it's reduced the battery lifetime. So if we need to understand how to improve battery, we need to find really how to design an optimum electrolyte and optimum material in this. So the problem here is why this is not possible currently. Most of these systems, as you see, it's very large simulations, and most of this has been done using the DFT. So I'm showing an example for simulation using DFT for cathode battery material and for two different properties. One here I show the voltage, and on this here I saw the volume change in the material. So here they did it for different function of the DFT. So, and the y-axis here is the difference between the calculated voltage from the DFT and the experiment, and the measurement. And so from that results here, you see that the function, this function here, produce a very good agreement with the experiment. If you look on this here, when we start to look at the volume change in the material, the function that has shown a good agreement with experiment for the voltage doesn't show the same for the volume change. And that's the problem with the DFT. It cannot be used for benchmarking. And so the experimentalists we need the experiment to really know which function to use. So in that case, that's why one of the main reasons why battery is really development in battery is very slow, because it's currently still relying on trial and error from experimentalists. So we need accurate tool here to be able to optimize those material. And the problem with the classical simulation is that accurate tools scale exponentially and has a very unfavorable scaling. And that's where quantum computing is more has this promise to bridge this gap between accuracy and efficiency. And that here is what I'm going to be discussing. So to start here, we start to look at these electrolyte decompositions. First, I perform some classical pre-processing. So we run this quantum espresso, and we have designed this half cell where the anode is made of the lithium metal, and the electrolyte is made of a combination of ethylene carbonate and dimethyl carbonate, and that's a commercial electrolyte used in battery for electric vehicle. And we run these simulations here. So you can see at the beginning here, this start to be absorbed on the surface, and then there's electrochemical reaction happen. And here is I look at this bond distance as a function of time during the simulation. So we see that within 1 picosecond here, this ring opening start to occur, and the formation of this CO gas happens. So to understand how this reaction happen, we start to look at the density of state. So in this case here, we look at the density of state of the anode and the LOMO energy of this electrolyte. So during before the reaction, so I show here that until 1 picosecond, nothing happened. And after that, a reaction happens. So during this time, what we observe is that always the LOMO energy of this electrolyte is above the Fermi energy level of the material. But then when the reaction start to happen, we observe that here the LOMO energy start to be degenerate with the Fermi energy. And that is actually when the reaction is facilitated so that electron can move from the lithium metal to the electrolyte. So in that case, we need to understand what is the energy needed for driving this reaction so that we can know how to design those molecules to suppress those chemical reactions. So that is what we need to learn to really accurately design, to compute accurately those energies, to learn how to design those materials. So for quantum, to start really modeling this reaction. So as you know, this is really very large systems, and we cannot really still simulate all that reactions. So what we did here is that we use here this from snapshots from the quantum espresso. And from these snapshots here, we define an active space. So to define the active space here, we use this AVS-DMET method. In that case, we selectively choose those orbitals that we want to use in the active space. And here we choose this 2p orbital in the carbon and oxygen for this molecule. And we choose up to 12 in these systems for this problem. We simulate for 12 electron and 12 orbitals. Of course, you can scale this up and make it more complex, and that will be for future. Is that you can also include the first layer of this material as well in your active space for the problem. Yeah. So this is the classical pre-processing. I will go in the now. Okay. So this all is just classical pre-processing for this problem to start here. So once you have this, now once you define your active space and then this problem, then you start to encode this into the quantum hardware, into using CUDA-Q. So in this work, so the first thing is that to define what is the ansatz, and I will show different algorithms here. So just, I'm not gonna go in details about VQE. You all discussed it yesterday. So, but here in general, using this VQE with the UCCSD, and this is in this case, this is the ansatz used to for your wave function, and you find the optimum parameter of this UCCSD that will minimize this Hamiltonian. So this is a kind of a brute force method that people have been using. But we also here start to look at the generative quantum eigensolver. So this is the method that, so all this work from here start to be done on perimeter. So I wanna, sorry that I didn't forget this part, but that's all on perimeter. So this method is actually here we are using as an AI to generate this quantum circuit. So in the VQE method, it's a brute force, you have the UCCSD, you optimize the parameters on the quantum circuit. In the generative quantum eigensolver here, that's actually not the case. So in that case, you have UCCSD are your pool operators, and then you have the generative model is actually sampling from this pool operator. And the parameters that are optimized, so depend on the sampling and the loss function you have in the GBT, you are in this case optimizing the parameters in the neural network of the generative model. So now you are not optimizing any parameters in the quantum circuit itself. And you can train this to find the optimum circuit of your problems and then design the circuit. In that, and so that you can overcome many problems you have now in the VQE. So here is actually a little.
Then you must have a guarantee that the minimal of the cost function of the neural network, the classical neural network, is the same minimal as the circuit.
I will go on this slide, next slide. So how it's working, and come to your question here, is that so during the training of the neural network, so you have your pool operator, so it will sample from this pool operator. And whatever you sample from this pool operator, you use to compute, so this is during the training, you use this on the quantum circuit to compute the energy. And then you compute the loss function. The loss function here in this work is defined as the difference between the logit, in this case, sample the energy from your GBT model and the computed energy from this quantum circuit. And the difference between them give you the cost function. So in that case, you are you are letting the GBT model to learn how to design a quantum circuit that will match the energy obtained from the quantum circuit. So this is a little bit also not, I would say here's what we have done in this work is just a proof of concept now, because when you do this, it's not when you like letting the GBT model to learn the energy obtained just from the quantum circuit, you might not necessarily obtain the minimum energy because you are just making the difference here. And that's work in progress we are doing now. It's just gonna sample a quantum circuit that will match the energy of the quantum that computed from the quantum circuit, but it's not necessarily, it's not the minimum. But that work is in progress to really improve that.
And so do you need data from the actual QPU to do the training?
Yeah, that's what's here. So
Okay.
that is actually the energy here. So what it happens is during the GPT, so that's only happened during the training of the GPT. So it's generate a kind of like, you know, in this case, the unitary operator is defined as your token in that case. And in that, and the GPT is trying to find the sequence of this token. And then it generate a kind of sequence. In this case, it's a document, but it's what is the sequence is give you the circuit exactly. And then whatever you obtain from that, you use this on a real quantum hardware or in a simulator to compute the energy. And then the difference between what you obtain from the actual quantum simulation and what you obtain from the predicted from the GPT define what is the cost of function. And you keep training this until the GPT learn to design this circuit that will match the energy obtained from the actual quantum circuit on the real quantum hardware or on simulator. So here's the result that we obtained. And here I compare the energy from quantum GQE method and VQE using this UCCSD and against the classical couple cluster method and the CASI, which is a full CI in the active space. And here we were sampling, as I said, we took a snapshot from this molecular dynamic simulation to sample this reaction. And so in general here in this figure, we observe the same like expected from this chemical reaction. It's an endothermic chemical reactions. And that's what's known in this from available experimental data as well. And from this, actually, here we can learn how much energy is needed to go from this, so for this molecule to reach to this transition state that allows this reaction to be happen. But of course, this is just really a simple simulation for this system. Of course, in that you have to account for a lot of things that's here is still missing. But qualitatively, that produces the trend that we know from experimental data. The other thing here I want to mention is that how a GQE method will be really quite helpful compared to the VQE, because here you can see how much time, so here for this unitary operator, so if you use the brute force method with the VQE where you have all the UCCSD, and so you have everything, you see that you have the number of the unitary operator here for this 24 qubits is 14,000. But here for the GQE, I compacted this up to just only 30 unitary operator. And the thing here also for training for this GQE, it's very quick. It takes like minutes to train this model to have this answer, compared to the VQE, which takes really weeks for this kind of simulations. Another advantage here is that also you might hear in this previous talk, he speak about parameter shift and things like transferring information from one model to the other. In the GPT model, it has also this kind of thing is that you can actually let this GPT model to train on some different molecules, and you can, after that, transfer this to another molecule that it haven't seen before, and it can predict for you the circuit. So that can actually save a lot of these iterations that we have and the problems that the VQE have currently. But of course, there is a lot of work still to be done on this GQE. It's just a proof of concepts that we show it work. And you will see a lot of papers after that coming out on this direction. So yeah, with that, I would like to conclude here. Yeah, so we think like, yeah, quantum computing is going to be helpful for a lot of for application like in battery materials, which is really going to be useful for automotive industry and for large scale applications. We have used NVIDIA CUDA-Q to model this system for electrolyte decompositions with 24 qubits, which is the largest to date for these systems. We have investigated. And yeah, another thing is that also with CUDA-Q, one of the main advantage here is that you can, if you want to run this on a real quantum hardware, you don't need to really modify anything. It just whatever you wrote in your code, it's gonna be executed on a real quantum hardware. So you can test it today on a simulator, but when you have access to the quantum hardware, you don't need to change anything on your hardware, in your algorithm. And yeah, thank you.
A few questions, but before I go to the studio, there is a question online. I don't know if you can read it or I can read it.
Can you read it?
Yeah, so I think when you go back to the previous slide, the question was, which data were you used to train this model? Like what specific data you used?
So the data that you are using is the unitary pool operators. So in that case here, I have the UCCSD pool operators, and I use this as my data for the training. So in that case, the GPT model during the training is going to sample from these unitary pool operators, and this unitary pool operator, after you sample this circuit, you use this circuit to compute the energy from the quantum circuit, from the actual simulation, and compute the cost function. So the data here is the unitary operator of the problem. Here I use the UCCSD, but this can be also extended to any other. So for example, you can use the generalized single double or the QAOA, for example, as well. So it depends on the problem answers.
But the actual data is also the energy that you got somehow, but it's a simulation
So
energy.
the energy is that's what you use when you are using the training to define the cost function, because you have to train the GPT model for a given task. So, and that can change depend on the problem you are investigating. So.
You say, what is like the size of these GPT models in terms of number of parameters? And do you see any evidence that the size of the GPT model needs to scale with the number of qubits for the circuits?
That's a good question. So here we are using actually the standard GPT model. I think the number of parameters there, like probably I don't know, million of parameters there. So that, and now the second thing is that depend on the parameter, I don't see a number of qubits. So I don't, to my best of my knowledge, I don't think so, because what you are doing here is, now the unitary pool operator you are generating is your data. And we know that GPT model currently is training on million of data. Actually, the more data you have, the better. So in that case here, like million of, I mean, when you have like the unitary, like if you have 100 qubits, if you have, I think that might end up like, I don't know, 100 probably of unitary pool operator. I don't think this is a problem in getting the GPT model at all.
Go ahead.
I'm looking about so if you can match the output of the GPT model, then why do you use the quantum circuit? Why not just use it?
For the training, because how the GPT model is going to know, because now you can generate a kind of circuit, so it will generate some circuit, but it can be whatever. So you need to teach the GPT model. So because the GPT model has some parameters here, right? It's the neural network. So you need to find how this, you need to teach this neural network to be optimized such that it learns how to generate a circuit, a good circuit for your problem. So how you do this, you must do the training first. And during the training, that's where you need to compute the energy so that the GPT model learns how to find that way and optimize the parameters to do that.
Then when you run it, you will generate a new circuit for a new model.
So for every model, yes. So for every model, currently the way it works, for every model you have to train it first, and then after you train it, you will have the final circuit. But that is fast because all the training is happening. The parameter is on the GPT model, it's not on your quantum circuit.
I guess the question is then why do we use the quantum circuit? If you have a GPT model that's spitting out energy that would the quantum circuit itself will give you, why not just use it?
Yeah, but how you're going at the beginning for the training, you must do this on a quantum circuit because the GPT model doesn't know how to design this circuit. Like it doesn't know. You give it a problem and if you run it now, it has a camera, you initialize the GPT model by random parameter here. And so it will generate some random circuit. The problem is that this circuit it's gonna do whatever. It's not making any energy. So you have to train the GPT model. So and to train that you must do this on quantum hardware to do this kind of function.
We have a couple more questions online, and then we can move to the next.
Yeah. I was going to say, you said training matching circuits to energy.
And then what you want in the end for solving your chemistry problem is the ground state energy, right? And so you just go and ask your GPT, now that you've done the training, give me the circuit that you give me the smallest. And
That is what is happening. And actually, that's also the goal for future things, is that not just for the beginning. So now it's training, and now I don't need to find it. Then I just don't, and I do my final, and that's done. The good thing is that now that's why will work is that how we can transfer this for another model. Because already trained the GPT model on something. So can we transfer this to another model? Because this is happening already in class optimization, so we do some kind of things like that. But it's not obvious yet, but I think there's a lot of work to actually happen on that very stage. It also, it would be great to find a way of how we can do something that haven't seen before. So that would be something for I think.
so you said that's what I mean, MC is biased, right? So that's sort of no guarantee that I'm the best circuit or that I'm the best circuit is one that is how successful is it? For example, now that like you've done that training in class, like what's a circuit to use best energy, right? When you run that new circuit, is it actually that close to the one that was predicted, or like if you try to compare maybe on toy problems where you know what the ground state is going to be, like how close is that? Like,
Yeah, that's also a good question. So that's actually something is still under experiment. So yeah, we now know because we know the actual results, right? Without knowing the actual results, how the GPT, it might give you a circuit that it could be closer. But even, yeah, I think that would be require some work. But I think even if not, I see the vision for me for that is that it still can really accelerate things, because even if it gives you something, you can run a BQE, which is going to be shorter, and also you have a compact circuit. So I'm sorry.
And more questions during the coffee break?